This block diagram shows how memory interface generator connects multiple Axi masters inside an FPGA to an external DDR memory. On the left side, there are multiple Axi master components, such as a microprocessor, DMA engines, or custom logic blocks. They act as data sources, and they need to read or write to external memory using the Axi protocol. Between the master IPs and the MIG, there is an Axi interconnect that makes it possible to connect multiple masters to a single slave port. It handles arbitration, routing, and timing for multiple concurrent masters. The MIG can be divided into the three different sections. At the highest level, the MIG provides an Axi slave interface that receives memory transactions from the interconnect. It converts Axi read and write requests into internal DDR controller commands. DDR controller is the heart of the MIG and is doing the main duties. It manages DDR timing, burst access, bank switching, refresh cycles, etc. Physical layer interface converts controller commands into physical signaling required by DDR. The word soft here means that the PHY implemented in FPGA fabric, not as a hard IP block, or it doesn't exist on board on the PCB. Whenever logic needs to communicate with an external device, a PHY is required to convert the logic commands and data into signals compatible with that device. The MIG also provides multiple necessary signals in the PL side. The first one is calibration done. This important signal indicating that MIG's internal calibration is complete and the memory is ready to use. The MIG also provides a clock that must be used by all logic modules intending to communicate with it. It ensures the synchronous operation among all the IPs. It provides a synchronous reset signal as well, which is used to reset the Axi bus and other connected peripherals. The yellow double arrow in the diagram represents the bidirectional physical interface between the MIG and the external DDR memory module. In reality, this is not a single wire, but a complex bus made of many different signal types, each with a specific purpose. I selected the AC701 evaluation board as the target platform for this design. Since I'm working with a Xilinx evaluation board, Vivado provides several default examples designs in the board window. For convenience, I can simply select the DDR3 SDRAM example and drop it into the block design. Vivado automatically configures all the necessary components for the MIG, saving a significant amount of time. Let's take a look at the Memory Interface Generator wizard to examine the configuration. If a Xilinx board preset is not used, all of these settings would need to be configured manually based on the board's datasheet. As shown here, parameters like memory type, clock speed, data width, reference clock, and others are configured directly within Vivado. The DDR bus interface requires around 120 pins, including data lines, strobes, and control signals. Using the board files, Vivado automatically assigns these pins correctly, greatly simplifying the setup process. Let's review the MIG ports quickly. Differential input clock. This is the external system clock input in differential format. It is used to drive the internal MMCM in the MIG to generate required clocks for DDR3 operations. System reset. This is active high reset input that resets the MIG logic. It is typically derived from a board-level push button or processor system reset. Axi reset port, an additional reset input used in Axi or control paths. External DDR memory bus. This bundle connects directly to the DDR IC on your hardware. It contains address lines, data strobes, control signals, and clock. User interface clock. It's the main operating clock for logic that drives or reads from the MIG memory interface. Your logic must be synchronous to this clock when driving or reading from the MIG's Axi or native interface. Typically generated by MMCM based on DDR clock, and its speed is 100 MHz or 200 MHz. Synchronous reset. This is a reset synchronized to user clock. Use this for resetting user logic interacting with MIG. MMCM locked. Indicates whether the internal MMCM has locked onto the input clock. Calibration completed. MIG uses this signal to indicate that DDR memory initialization and calibration are complete and the interface is ready. Ensure this is high before issuing any memory read and write transactions. For the reset pin, I'll use the CPU reset push button, which can be added to the block design from the board window. The second IP block to add is the Axi interconnect. Set the number of slave ports to 1, and set the number of master interfaces to match the number of data sources in your design. Connect the interconnect's master port directly to the MIG slave port. We need to create a synchronous reset. To do this, add a processor system reset block to the design and connect the MIG's MMCM locked and user reset signals as its inputs. In this design, 2 Axi traffic generators are used as data sources. For simplicity, select high-level traffic and set the data profile to data. This configuration removes the slave interface from the traffic generators and simplifies the design. In the Axi options, enable address swapping. Later, you'll set the base and high addresses according to the address assigned to the MIG slave port. The first traffic generator is used exclusively for write transactions. Add another traffic generator, and this time, configure it for read-only transactions. To control the start and stop of the traffic generators, use a virtual I/O block. The first 2 outputs will be used to control the start signals, and the third will control the stop signal. Connect all clock inputs to the MIG's user clock and connect all reset inputs to the processor system reset output. Validate the design. After validation, check the address editor to confirm the assigned addresses and use these values to configure the Axi traffic generator's base and high addresses. Right-click on the traffic generator's master output ports and enable the debug option. Vivado will automatically insert an ILA and connect it to the master ports. In the ILA's Interface tab, set the maximum number of outstanding transactions to maximum. For debugging purposes, also add a probe to the calibration done signal. Now we're almost done. Add a top wrapper to the design. If you're working with a Xilinx evaluation board, proceed to generate the bitstream. Once the bitstream has been generated, download it to the board. You should see that the MIG has completed its calibration successfully. You can now control the read and write transactions using the virtual I/O dashboard. First, try the write transaction. Writes will occur in sequence. Next, run the read traffic. You should see successful read responses. You can also try running both read and write transactions simultaneously.